In this video we will be looking at relational databases. So a database, really important definition to learn. A database is a persistent, organized store of related data. Now what we mean by persistent is that it is permanent, and what we mean by organized is that the data is stored in records and fields. Now it could be a single table or it could be a collection of tables. And it's really important that we understand how we can design databases and program databases, because most programs will store data using databases, and we need to make sure that we store data in databases so that it is external to the coding of the program, if you like. So we'll look in this topic over the next few lessons at relational database design, at normalization, and also at SQL and how that's used to program and access databases. So some important database terminology that you need to be aware of. You need to know that a table is a collection of data that relates to an entity. So an example of an entity might be students. A record is a collection of data about a single entity, so a student, for example. Field, that's like the column of a database. It's a unique piece of data about an entity, so it might be a student's surname. And a field name is an identifier for a single piece of data, so it's the column name, if you like. So when dealing with databases, we talk about entities, we talk about attributes, and it's really important that we understand what they are. So an entity is something in the real world that we store data about. It could be a person, it could be a car, an order, or maybe an exam subject. These are all examples of entities, and an entity becomes a table in a database. So once you've thought about an entity that you want to store data about, that would then be stored in a database table, and one instance of an entity in a database is a record. So within that table about your entity, an instance of an entity might be would be a record, recorded as a record in a database. So if you consider people as an entity, or students in a class as being an entity, then one instance of those students would be a student, and that would be stored as a record. Now an attribute is a characteristic about an entity. So it becomes a field in a database, it becomes a column in a database. So if the entity was students, for example, then an attribute might be surnames. Now a database doesn't really do anything on its own, it is just a store of data. Now in order to actually handle the data, we use data handling software, and it brings the database to life. So the software might be a dedicated data processing program used to access customer details, or it could be a computer game which needs to update the game's high score table. But whatever the case may be, the software needs to accompany a database to enable the database to be created, for the data in it to be retrieved, updated, and deleted. And that comes as a little acronym, CRUD. Now, a database management system. This is kind of what the actual applications, the programs will really use to access data within a database. So a database management system can be thought of as an intermediate program, sort of sits between the database table or tables and the application itself, and the whole point is to separate the database from the application that uses that database. So here's a little diagram to show that. You've got your database at the bottom, you've got your applications, and we've then got in the middle our database management system, which will be able to actually talk to the database and retrieve the data, delete data, create new tables, and so on. So why do we actually need that sort of separate system? Why do we need the database to be separate from the program? Well, the database management system, you can think of it as like a guardian of the data, so that any application that needs to access the data has to do it through this guardian, has to do it through the database management system. And the reason for that is that it can ensure that applications handle the data correctly. or in other words, it can prevent applications from handling the data wrongly, which could compromise the integrity of the database. And it also means that if the code of programs are edited, then programmers don't need to worry about compromising the data because it's separate from the data from the application itself. So what sort of features are there in a database management system? Well, one thing which is really important is it can allow different applications to access the same database at seemingly the same time. It controls access to the data, so it can provide security that provides limits to what different applications can do and what different users can do, for example. It can provide backups and the ability to restore from a backup. It supports query language. So these are languages that can allow you to extract data from a database, maybe add or amend data, maybe alter the structure of a database. It can enforce something called referential integrity. Now that's something that we'll discuss later on in this lesson, but really what it means is that it stops there being any instance where relationships between tables could be damaged. So for example, if you had a database with two tables, one for the students and another table for different exam subjects, there will be links between those tables. So a student might be taking one particular exam subject, another student might be taking another exam subject. Now if you were to delete a particular exam subject, that would cause a break in the link between the two tables, and that would not be good. So we have referential integrity to ensure that if, for example, something in one table is deleted, that then that's updated across all tables where there are links. It also controls something called concurrency. So this is where data, two different users, for example, might be using the same data in the database table, and the database management system can lock down the data while someone is working on it so that someone else can't change it at the same time. Now, database management systems, we said before that it supports query language, and this is a really, really important feature because with query language we can actually start to manipulate data in a database table, or start reading it, deleting it, updating it, and so on. So query languages, they are just a set of commands that applications can use to talk to a database. They will allow for CRUD, where you can create tables, retrieve, update and delete data. And SQL is the most common language that database tables will be queried with. Now when we talk about retrieving data, we're really talking about querying the database. So asking the database questions and trying to find related data to that question. So for example, we might want to query the database which will show us all the students in a particular class, and the database would then respond by presenting only those students from those classes. So querying is asking questions of the database. It's retrieving only certain specific bits of data. Okay, so as I said, querying, it's asking questions, it's at the heart of working with databases, and we'll have a little look at that over the next few lessons. Now, when it comes to database design, we've got flat file databases, we've got relational databases. So it could be a single table, that's a flat file, or a collection of tables that are all linked together, and that's known as a relational database. And the choice of database design that we have depends on the entities that the data is about. So here's an example of a computer shop sales flat file database. So here you can see that we've got different records for each order, and within each record we've got the customer name, their address, and the item that they actually purchased, and the data which they purchased it as well. Now the issue with having a database table like that, where we've got multiple entities in a single table, we've got customers, we've got products, they're all together. The reason why this is an issue is that if you consider a new sale occurring, a new record would have to be added. Well, that's fine, but all of the data about the person and all of the data about the sales item would have to be added each time. And that brings us a problem. It takes time to repeatedly enter the same data into a database. So for example, if the same customer came to the shop 4 days later and then purchased another item, you would have to write out in that database the same customer information, which takes a long time. And also, you might have over several days lots of people buying the same item. You would have to actually write that same item onto separate records of the database over and over again. So it takes time to do that. The other problem is that humans make mistakes. So if you have to enter the same data over and over again, almost certainly there's going to be some little errors that creep in somewhere, and that's going to make the database really difficult to search. For example, if you're trying to find all the items that Joe Bloggs had purchased, if you spelt blogs wrongly somewhere, then obviously that data isn't going to be found on a particular search. And also, if an update was made to the customer's data, for example, I don't know, let's say Erin Bloggs got married to Mr. Jones, you would have to go through all of the records where that particular custom is and update the surname to Jones, and that would take a long time. All of that is not efficient, and we need to be as efficient as we possibly can be. So what do we do about it? Well, when we've got more than one entity, we need to start considering database designs as having more than one table. So the entities in the database have a many-to-many relationship. A customer can buy many items, and an item can have many different customers. And this is shown in this what's called entity relationship diagram. So that is just saying that customers can purchase many items or have many items, and an item can have many different customers. Now, many-to-many relationships, we've always got issues in flat file databases because they generally require the need to duplicate data over and over again, which leads to data redundancy. And that's what we've just discussed. The fact that in a flat file database, you might have to be repeatedly writing in customer details and items over and over again, and that's really inefficient. So what's the solution? Well, I've already sort of touched on it. We have to have separate tables for these entities. So the way around the issue is to make 3 different tables of the data. We need a data table, for customers, which is one entity. We need a table for the items, the products, that's another table. And because it's got this many-to-many relationship, we also need one more table, and it's called an intersection or junction table. And it's all to do with the fact that we've got this many-to-many relationship. And in this case, the most sensible intersection table would be an orders table, because ultimately customers, when they purchase an item, they've placed an order. And then we can link these tables together. And the idea is that with this setup, the customer details and the product details only ever need to be entered once in their own separate table. Then each time an order occurs, all we do is we link the appropriate customer and the appropriate item to a record in the orders table. It means that we don't have to repeatedly enter details about customers and products, so it's much more efficient. And if we wanted to update the name of someone in our customers table, that would only need to happen once. So it says here that if the same customer makes another order, their details are already stored, and so by linking them to a new order record means that we don't need to keep entering the same data about the customer for each sale. Therefore, there's no time wasted entering duplicated data, reducing the chance of introducing data errors and improving the efficiency if a customer or product detail needs updating. So let's actually have a look at this in a visual way. So here we've got our customers table. So the previous table has been split up now into 3 tables. We've got our customers table, which is all the information about customers. We've got our products table, which is all the information about the products. And then we've got our orders table. And you can see that each record of our orders table will link a customer and an item and then have a date when that took place. So there's our customer table, and there's the link to the customer ID column in the orders table. And there's our products table linking to the item ID of our orders table. Okay, so key fields are really important in relational databases. We have to have a good understanding of key fields. So to ensure that the relationships between the tables are fully functional and they're effective, each table has to have some key fields. Now, a primary key, every table will need to have a primary key, and that is simply a field which can be used to uniquely identify each record of the table. So a primary key must contain some data which is different in every single record, and usually we achieve this by using an ID number for each record. So where an entity has more than one field, that could be used as a unique identifier. If one is taken as the primary key, the other one can be used as secondary keys. And then if we've got this relational database structure where we've got, as we saw before, this intersecting table, this junction table, where we actually have links to the keys of other tables, these are known as foreign keys. So they're attributes of an entity, so fields of a table that link to another table. In other words, a foreign key is a primary key from another table. Now that's best understood by having a visual example, which we'll have a look at on this slide. So here you can see that we've got our primary key in our customers table, items table and orders table as being, well, in the customers table it's the customer ID, in the items table it's the item ID, and in the orders table it's the order number. So each of those are primary keys. They are unique, they have unique data for each record. So no two records will have the same ID number, no two records will have the same order number. But then over here in our orders table you can see that we've got customer ID and we've got item ID. Now customer ID is a foreign key because it's actually the primary key of the customers table in a different table. So you can see that the customer ID here, okay, that primary key is being used, okay, in the orders table, therefore it is a foreign key. Okay, so fields in a table that contain data from another table, usually the other table's primary key, so to form a link between them. It's the same over here with the ID for the item. We've got the item ID as the primary key of the items table. It is a foreign key in the orders table. And it is there so that a link can take place. Now we said what queries were before. Remember that queries are just making sure that we can interrogate the database, ask it questions, finding and retrieving data that we are looking for. Now, with a single table, it makes sense that we can look up bits of data. But what's really important to recognize is that in a relational database, the data about a particular sale, for example, is stored in several tables because of the actual relationships, because they're all linked up. So whenever we start querying relational databases, the computer will treat it as one big table and it will follow the links to find the data that's needed. So most of the time a database isn't just about storing data, as we know. It's really about using that database to retrieve things, to find things out. And searching for information from a database, as we've already learned, is called querying. And because of the relationships, we can easily run a query and find related data as if it were one big table due to those links. Now, when we produce relational databases, we have to consider what the entities are that we want to be making this database about so that they can go in their own tables. And we also need to think about what the relationships are between these entities so that we can work out whether we need to have an intersecting table, a junction table, like we saw in the previous example with the orders table. So at database design level, to avoid issues discussed in previous slides, we need to think about the entities and their relationships, and we use ERDs, entity relationship diagrams, for that. We've already seen an example of it. Now there's three different ways which entities can relate to each other. You can have a one-to-one relationship. For example, we could have this here, husband and wife, as two entities. A husband has one wife, a wife has one husband, or should be the case. We've got, or a wife could have one wife, or a husband can have one husband. Anyway, hopefully you understand what I'm trying to get at. One-to-many relationship. So we could have a school that has many students, and we have a student that has one school. So that is a one-to-many relationship. And we could also have, when we discuss entities, we could have a many-to-many relationship. So we saw this example before. A customer, can have many different products, and a product can be bought by many different customers. So what we've already seen is that many-to-many relationships will not work in a database, and so they will always need an intersecting table to satisfy their relationship, so that the database can function properly. So we add this intersecting table to ensure that we remove the many-to-many relationship and turn them into two one-to-many relationships. So when we design a database, each entity should have its own table. We know this. For one-to-one and one-to-many relationships, the tables for each entity can be linked directly. That's fine. And for entities that have many-to-many relationships, the tables cannot be directly linked, and so we need an intersecting table so that we can create two lots of one-to-many relationships so that entities can be directly linked. So here we've got our direct link. One-to-many, we've got our direct link. We cannot have a direct link on a many-to-many relationship. It means that the database just doesn't work. So we turn this relationship into a one-to-many relationship and another one-to-many relationship by introducing this intersecting table. Now, referential integrity, we've talked about this a bit earlier. So we've already seen that we've got lots of different tables in relational databases, and they're linked in different ways. And it's really important that a given element in one of these tables that links to another is not deleted, because it will cause a break in the relationships between those tables and cause a problem for how the database functions. So referential integrity is this concept that relates to relational databases, and it states that all primary key values match those of a foreign key to which it's directly related. So what that actually means, if you were to put that into sort of a layman's terms, if table 1 contained a field, so a foreign key, that links to a field in table 2, which might be its primary key, referential integrity would stop the addition of a new record in table 1 which can't be linked to table 2. Also, if you wanted to delete a record in table 2, all records in table 1 that are linked to this deleted record would also have to be deleted to make sure that we've got this referential integrity. So usually words don't quite cut it, so let's have a look at a visual example of this. So we've got table 1, which is the orders table, we've got table 2, which is the items table, and what we're saying here is that referential integrity would stop the creation of a record in table 1, so a new order, for example, which doesn't have a link to table 2. So if there's no item in table 2 that could be added to a new order, then referential integrity would stop that new record being created. And also, if record 1 in table 2, so for example the monitor record, so item ID 1, monitor, and 100, if that record was to be deleted, to ensure that we've got referential integrity across our database, we would have to then delete records 1 and 4 in table 1. So order 1 and order 4, which both contain the monitor item, they would have to be deleted as well to make sure that all tables are consistent. And that's referential integrity.